Now we'll see more examples. So to begin with, let's consider the integral from 2 to 6 of 1 over x minus 2. Importantly, notice that this function, 1 over x minus 2, has a discontinuity at x equals 2, which happens to fall on the left edge of our interval. So we said that we could now treat that as a limit. So I'm going to have the integral now of my 1 over x minus 2. My upper bound is still 6, but I'm going to write this as the integral from t to 6, and I'm going to let now t approach 2 from the right. Now, the antiderivative here is going to be, let me write this here, the natural log of the absolute value of x minus 2, and we're evaluating this from x equals t to 6. So this leaves us with the limit as t approaches 2 from the right of the natural log of the absolute value of t minus 2, t minus 6, minus the natural log of the absolute value of, this is the natural log of 6 minus 2 in the absolute value there, minus the natural log of t minus 2 in absolute value. So I'm taking the limit of this whole expression. Now the first part is natural log 4, which is not problematic. And here I'm letting t approach 2 from the right. So we're looking at the natural log of positive values where those values are approaching 0. So thinking of a sketch of the natural log function, we're essentially traveling along this graph toward 0 from the right. And I can see that that part is going to approach minus infinity. So because this is not a finite limit, we can say that this integral diverges. Another example, if I have the integral from 0 to 3 of 1 over root 3 minus x. Again, this is has a discontinuity at x equals 3, the rightmost point on our interval. So we express this as a limit as t approaches 3 from the left, and we're going to integrate from 0 to t, and I'm going to write this as 3 minus x to the minus 1/2. So the last step is, again, to deal with the limit. The antiderivative here, I'm going to have 3 minus x to the positive 1/2. I'm going to multiply by 1 over 1/2, or 2. And then I also have to have a minus sign because of this. So again, I could have used a u substitution to make that a lot more clear. But if we kind of reason through it, we can see that we need this multiplier of minus 2. And you could check with the chain rule to see that we get back to 3 minus x to the minus 1/2. We're evaluating this now from 0 to t, where we're letting t approach 3 from the left. So plugging in these bounds, this leaves us with maybe -2 that I'll factor out. And so we're going to get square root of 3 minus t minus the square root of 3 minus 0. And unlike the example above, notice that now as we let t approach 3 from the left, we have, again, positive values under the radical that are approaching 0, but that limit's just going to be 0, which is fine. So we're going to get 0 minus root 3 in parentheses there. So we actually get a finite limit of 2 squared of 3. And we could say that this integral converges, in particular it converges to 2 root 3. And then to deal with one where the discontinuity is in the middle, we can look at 1 over x squared being the integrand. It has a discontinuity at 0. So if I'm integrating from -1 to 1, here's an example where the discontinuity is in between the edges of my interval. So of course it doesn't have to be exactly in the middle like this example. It could be anywhere as long as it's not on the edges. So we said that what we have to do is split that integral into 2 pieces, and we have to split it at the discontinuity. So in doing so, I can treat this as a sum of limits. So I'm going to have the limit as t approaches 0 from the left, and I'm going to integrate from minus 1 to t. And then I'm going to add that to the limit as t approaches 0 from the right and integrate from t to positive 1. In doing so, our antiderivative is now going to be minus 1 over x. So in one case, we're integrating from minus 1 to t. And then in the other instance, same antiderivative, but integrating from t to 1. And so what this leaves us with is we have the the limit as t approaches 0 from the left. And in that case, we're going to get negative 1 over t minus a negative 1 over a minus 1. So that's going to be 1. Plus the limit as t approaches 0 from the right of negative 1 over 1 minus negative 1 over t. So in both of these instances, notice that if we were to think of the graph of 1 over t, and I'm approaching 0 either from the left or the right, we're going to get plus or minus infinity. So what we're seeing here is that these pieces are problematic. And in fact, I only need to look at one of them. So I could notice here that if we think about, so I guess I graphed 1 over t, but you could graph minus 1 over t. Essentially what's going to happen is that these are going to yield infinite values. And as soon as I see that this limit does not give me a finite limit, I can stop regardless of what I find with the second one. And I'm going to be able to say that this integral, again, the one I started with, diverges. And this is because the only way it could converge is if both of these limits existed and were finite. And I can see right now that the first one doesn't, and I can stop short of even looking at the second one and conclude that this integral diverges. So you'll get a lot of practice with these with the textbook problems. Again, I really encourage that. So you'll see that sometimes you can have this discontinuity in between the edges and the integral can converge. So a discontinuity in the middle of your interval does not necessarily mean that it must diverge, but it does mean that we have to be cautious. And you'll notice that these types of improper integrals that deal with discontinuities of the integrand are a little bit more subtle and a little bit harder to spot than those where you can simply see infinity in the bounds. So you have to be a little careful. If ever asked to find or evaluate a definite integral, make sure to check and see if you actually do have any discontinuities over the interval in question.